NCAA presents Jim Bede, designer and builder of new types of airplanes for general aviation. His sensational bullet-shaped Bede 5 has become one of the most publicized sport airplanes ever introduced. Here on videotape, he discusses topics common to all aircraft design.
This tape is going to be on aircraft control surfaces. When designing an airplane or improving a particular design, there are a variety of variations that can be made to the airplane's control system which will allow the pilot to have adequate control. It's not really too difficult to come up with some form of elevator and stabilizer or ailerons or anything else that will give the pilot reasonable control through most of the flight regimes. Back in the 20s and the early 30s, most airplanes had systems on it that worked. But from what actually is capable of controlling the airplane to what is considered good flying qualities is a great deal of difference. It can be done. The science is good enough. The knowledge that we know about airplane designs and control surfaces are now good enough that we can actually put a great deal of effort in the design of the control surfaces themselves and come up with real good flying characteristics. Obviously, one of the things we want to be able to do is have control so that we can make the airplane roll if we wanted to, or pitch up or pitch down, and yaw and so on. That's the obvious. What's really important, however, is to have the kind of stick forces so that when we move the aileron itself by pushing a stick to the left, we'd like to have a certain kind of force feel in that stick. We don't want it to be real soft in the beginning and then real heavy at the end. We don't want it to be real heavy and then real soft. We want a nice even gradient. So when we push a little bit, the force is a small amount. We push a little bit more, maybe twice as much, we want the force to be twice as much. We want a nice linear variation. Same thing with the pitch control fore and aft, and same thing with the rudder pedals. And of course, if we have a harmony so that the aileron forces are nice and light, so is the elevator forces nice and light, and the rudder pedals nice and light. It can be done where, of course, and you can fly an airplane, a pilot can learn to fly an airplane where the ailerons are light and the elevator is very, very heavy. But this is not really a comfortable airplane to fly. Now, besides just the usual stick forces and the stick force gradient, we'd like to have some response too. So that if you move the stick to the left a little bit, you get a little bit of roll, and you move it twice as much, you get twice as much, and so on. So the amount of reaction you get, the time period at which it reacts, and the amount and the rate at which it goes, that's real important too. So we can develop all three of these things. We can develop something where we have adequate controls in the airplane, so under all flight conditions, we have control over the three axes, and that the stick forces, gradients, are nice and in harmony with each other, nice linear type variations, and that the rate of reaction and the rate of response is something that is proportional and therefore comfortable to deal with. When we talk about control surfaces, we're really talking about three fundamental things. We want to have adequate pitch control, we want to have roll control, and we want to have directional control. There are two fairly good references I'd strongly recommend. One is the old NACA Technical Report 927, and another one is Perkins and Haig's textbook on airplane performance, stability, and control. That's published in 1949 by Willie and Sons. There are other books, of course, that deal with the subject and quite well, but these two are one that I would recommend because they have essentially all the information that a general aviation sport plane pilot designer would like to be able to cover. Let's talk about horizontal tails to start with. Now, when we're saying horizontal tails here, we're really meaning the control that will control the pitch of the airplane. And this is whether the tail's in the back or the tail is forward. Whether it's a canard airplane or a conventional tail in the rear configuration, practically all of the characteristics are the same. And where there's a difference, we'll try and point those things out. The standard type that we're familiar with is the elevator stabilizer. This is where you have either a fixed stabilizer with a movable elevator or an adjustable stabilizer with an elevator. This is quite common on airplanes built from the 20s and 30s and 40s and 50s on, and even into today. However, there are some limitations to a straight stabilizer elevator where the all-flying tail, which we'll talk about a little bit later, actually overcomes. But let's discuss the stabilizer elevator situation now and talk about some of the characteristics that happen on the controls, and we'll get a little better idea as to how this applies to other things. When we start talking about the elevator, we have to start talking about the nose shape itself. And by that what we mean is, if we look at the standard stabilizer, maybe this would be a case where it represents about 60% of the chord, and then we have the elevator taking care of the remaining 40%. What we're talking when we're talking nose shape, we're talking this shape right here. How you shape that has a big effect on what the actual forces in the stick is going to be, and how this elevator will tend to float as the whole airplane changes angle of attack. You can have a perfectly round shape with a relatively close fairings fitting here. You can have an elliptical shape where the hinge line is here, and you have something like this. This is narrow, and your stabilizer will come up over in this region in here. You can have, actually almost a triangular type shape. There are variations in here. When you look at the books, the textbooks, you'll see some of these different shapes, and you can see what the variation of it actually is. Not only is the shape of the nose sort of an important thing, but actually where the hinge position is. You can see, for example, that if the actual pivoting point is right here, very little of the nose is sticking forward, and therefore it will have very little effect on what the actual elevator is doing. But on the other hand, if the hinge point is quite a ways back, then this means that this, we'll have to take this out, this nose section now will move through a fairly large arc in here and actually start to stick above or below the surface as the control deflection is moving. And you can easily imagine, as this nose piece comes out of the region of the fixed stabilizer here, that the airflow on it will have a very pronounced effect on the stick forces that will be generated throughout the elevator itself. So the location is critical, and the shape of the nose is critical. Critical depending upon what you want. In other words, if you have a very small little airplane, something with a very small elevator on it, the same size pilot that's going to fly an F-15 is going to fly this little airplane you're talking about. Therefore, trying to reduce the elevator forces in there, the stick forces, is not really all that critical, because you've got a pilot that's very large compared to the size of the surface. But if you start to get into, say, a normal four-place type airplane, like a 172 or a Cherokee or something like this, this could actually become an important type of thing. We go back and look at the old J3 Cubs or something like that, where basically what we had was a steel tube here and a steel tube here, fabric between the two, then another steel tube, and fabric between the trailing edge, and our pivot point was right in here, and this is where our elevator would move through this kind of arc. And there was essentially no nose shape there. It had nothing to do with it. This was not much of an airfoil, just a regular flat rectangular surface with a round leading edge and a round trailing edge. And the forces in that surface really are quite high. Those of you who ever flew for example, a Piper Colt or something like that. Gosh, here's a relatively small airplane, but the forces in that elevator were just tremendously high. And here that airplane would go along at 70, 80, maybe 100, 105 miles an hour, and you had tremendous forces. If that kind of elevator would be used on an airplane that would go 200 miles an hour, the stick forces would be so tremendously high that it'd be almost impossible for a pilot to be able to get any movement out of it. Now, the stick forces that you get based upon the actual shape of the airfoil, the hinge position, nose shape, and so on, this is important, this is critical. It isn't only dependent upon, it's actually dependent upon where your CG location is on the airplane and the stability of the airplane. As an example, if you have an airplane of a certain design with a certain type of tail, and you move the CG back so far that it is all the way back to what is called the neutral point. So at this point, the airplane is neutrally stable. Well, then it means that if you took your hands off the control and let a gust of wind hit it or something like that, the nose would pitch up and it would stay there. It isn't stable, it's just neutrally stable. Well, obviously, if you move the elevator just a slight amount, you'll change the pitch of that airplane tremendously, so therefore it takes very little stick forces, even for something having a control surface like a Piper Colt would have or something like that, only because the stability of the airplane is so marginal. On the other hand, if the CG is further forward on any airplane, the stability goes up. Therefore, for any given kind of control surface of the elevator, your forces go up. So there's two separate things here. One is we're talking about what if you have an airplane with nice, desirable stability, not too much, not too little, not so marginal that you can't be flying along hands off and hit a gust of wind or something like that and not have the airplane come back to recovery, and yet it's not so far forward that your stability is like it's on rails and therefore won't move at all, and it takes tremendous force of the pilot to move the stick to do it. We're talking about normal stability parameters. Now once you have that, you still can have variations of the elevator size and shape that will then control what the forces are going to be. Now you need a given size elevator to have a given amount of control to move the airplane. For example, in a tail dragger airplane, FAA in certifying it sort of determines that you have an adequate amount of elevator if you could come in and land and flare with a 3-point. This is the most critical thing to do. If an airplane, a tail dragger type airplane, has enough elevator to hold the airplane in a 3-point position when all 3 wheels hit, and that tail is operating essentially in ground effect and with the downwash of the wing, then that elevator is big enough and adequate enough to handle all other conditions in flight. On a tricycle gear airplane, what you have to be able to do is go down the runway and at 8/10 V-stall, be able to pull back on the wheel or stick and lift the nose wheel off the ground at 8/10 the speed of the stalling speed. So that gives you a rough idea of having enough elevator. But having enough elevator is one thing. Again, the forces in it vary. Now, you'll see in most of the textbook, we're talking about hinge moments. And what they're really saying is what is the moment, the force times the distance, the average force on that surface times its distance it's acting through, reacting upon the pivot point, the hinge moment itself. Now, once you know that moment coefficient, you can then determine what the actual forces are going to be in the control cables all the way up to the wheel. And obviously, once you have a certain moment coefficient on the control surface, and the faster you go, the higher the Q, the higher the dynamics on it, obviously the forces are going to get higher. And you'd like that. You'd like to have an airplane so that the forces in the elevator are nice and light as you approach landing, but as you go faster, they get heavier and heavier, because at real high speeds, maximum cruising speeds, you don't want the stick to be so light that you can very quickly maneuver, because if so, you're going to pull quite a few G's on you and the airplane, and that wouldn't be good. And also, by having this variation that the forces get heavier and heavier in the stick as the airplane goes faster and faster, is a very good, comfortable feeling. It gives you the feeling of recognizing and understanding the speed of the airplane and the dynamics on it. So that's an important thing. You start to work with what about the hinge moments themselves. How do you reduce them, or in some cases, how do you want to increase them? In the case of the BD5, when we were designing the BD5, we had such a small airplane there with such small surfaces, we really had the opposite problem. We had to look at things, how do we design the control surfaces to have more forces than less forces? But it's only when you get into very tiny little airplanes like this that you have to worry about. Most of the time, what you really want to do is reduce the hinge moment, reduce the stick forces, so you have a nice, comfortable feel. All right, besides strictly the nose shape and the hinge position, another thing that can be done is sealing of the control surfaces itself. Now, sealing does several things. One, you can just put a simple seal. Let's talk, for example, like that Piper Colt, where we just have a fabric stabilizer and a fabric elevator. By putting a little seal between the two, we will increase the effectiveness of the elevator, or aileron even if it happens to be that, but we don't really change the hinge forces too much. But on the other hand, if we want to design a system where we have an internal seal, where we would have something that, well, let's take pretty close to the same example here. We have a stabilizer. And in this case, we would have a spar here, and let's move that spar relatively far forward. And we have the elevator. Now what we're going to do is put a structure in here with a fabric or flexible kind of seal. Now what this is doing is stopping all air from going from the top to the bottom. So as we deflect the control surfaces, as we would deflect this elevator in this direction in here, we will reduce the pressure on this portion of it, so this will be low, and we'll increase the pressure in here. And of course, if our hinge position is right in here, this pressure differential within the seal region will actually tend to help push that surface in that particular direction. Of course, back in here, there's a tremendous moment to want to bring the elevator back down into its original position, but this sealed and trapped condition in here can actually go a long ways in reducing the kind of stick forces you'll have in it. There are two things you have to be worrying about here. One, how do I reduce the hinge moment of the surface itself as compared to deflection? In other words, the surface is flying along at a fixed angle of attack and you change the deflection. That's variation of the hinge forces for the actual deflection of the elevator. But then there's another thing to consider, and that is, how about when the airplane changes its angle of attack so that the angle of attack on the stabilizer elevator is varying, changing with you, but you haven't actually changed the position of the elevator relative to the stabilizer. So you have not physically moved the control surface. Well, that variation will also start changing the hinge moment. So there are two things you have to look at here. One is the change due to angle of attack, and one is change due to deflection itself. In both cases, you want to have them close to linear, and you want to have them in a relatively positive direction. In some cases, you will have an elevator design where when you change a tremendous amount of angle of attack, the surface itself wants to float up. So actually, compared to angle of attack, you'll have go from negative hinge moments to positive hinge moments, which is not necessarily what you want. Most surfaces, however, as you're flying along, as you move it, as you change the angle that the elevator is moving, the forces will be always in a favorable condition. They're listed as negative from a hinge moment standpoint because that's the way the sign would be, but actually what it's saying is that you have a positive and proper kind of feel within the elevator itself. We can try to reduce the stick forces by having an elevator horn. These are little surfaces that would stick out way in front of the hinge point, normally out near the tip. We've all seen airplanes where the outside surfaces of the elevator will stick out in a position quite a bit forward of the hinge line itself. We could take a look at a sketch of something like that. Well, let's draw it just over here. We can have a basic top view of a stabilizer, and this would be the normal elevator here, but instead of having the tip coming over that way, we can bring a portion like this. So this portion here now moves with the complete elevator, and this portion here is considered the horn. Obviously, how far you stick that out, the further out it goes, the greater it has a moment arm to counteract all the forces that are acting on the elevator aft of the hinge line. This is a very powerful method for reducing the stick forces. There are some real disadvantage with the horn sticking out like that. For one thing, as the horn sticks quite a bit further forward, you can see with just slight deflection of the elevator, the horn itself will start to stick out into the airstream as compared to the nose section in here. So the effect of this aerodynamics on this horn will become apparent very, very quickly. And as you get into higher angles of attack or higher deflections on it, it tends to become less linear. This kind of a configuration, for example, has one little problem, is that as the angle of attack of the whole elevator stabilizer changes, it will go from where you have positive hinge moments, negative hinge moments at low angles of attack, and then positive hinge moments at high angle attack. So you get a little bit of control reversal there, and of course you can make your horn stick out so far that you'll actually have essentially no stick forces as you're doing the deflection. You have to worry a little bit about ice, for example. If the surface is real close or the nose is very close to the fixed stabilizer in front of it, it's very easy for ice to build up in there and jam the surface. Or if you're flying along through icing condition with the elevator trimmed at a deflection position and the leading edge of this is sticking out in the airstream, it's real easy for ice to build up in there. Some of these things have to be looked at and have to be carefully designed. It isn't impossible to do, but you have to be somewhat tricky and clever about how you work with these horns sticking out in that particular region. Another method of controlling it is with the trim tab. And of course, we can just take, again, a plan form view of the thing. A trim tab will be nothing more than a little tab that will be put onto the elevator itself. And, well, we can show from a side view here. It will be just another movable little surface that we can put on there. And obviously, with the trim tab, we can sit there and have it controllable from within the cockpit, so we can actually have a control mechanism that we turn or pivot or rotate, and we change the position of this tab. And as we change that, that's going to obviously change the neutral position of the elevator itself. That's what would be considered a straight trim tab. We can have a ground adjustable one where you would just sit there on the ground and deflect it and set it. And of course, once you set it, that's the way it's stuck for the rest of that flight until you come back down and change it. That'd be a fixed trim tab. Those kind of things are strictly used for trimming the airplane itself, for your particular CG condition and everything else. And when, of course, what you've really done is if you have a trim tab on this kind of surface and it's at 0, the elevator will tend to float right at 0. If you, on the other hand, have the tab and you deflect it somewhat, you'll end up with maybe a condition like this when you trim the tab down. Now what you have done here is you let go of that stick, and that surface will actually find a central neutral position right there. The elevator is deflected, the tab is down here and it's down there. And what is done is generated some force, and then in this particular case it would be an additional total force on the tail downward. And maybe that's what you wanted. Maybe the nose felt a little heavy. You adjusted the trim tab to put more download on the horizontal tail to get rid of the nose heaviness that you were feeling within the stick of the airplane itself due to the CG location or your speed that you were flying at. But we can take these ground adjustable trim tabs or the cockpit controlled trim tabs and actually make either servo tabs out of them or anti-servo tabs. By a servo tab, what we're saying is this: we can link this tab itself in such a way that when we grab the wheel or the stick and we pull back and we deflect the surface in this direction in here, this tab itself will deflect in this direction. Therefore, the tab is producing an upward force to counteract the normal force that's trying to bring this complete elevator back down to neutral. So it's like a little servo motor or some little helping device. It's actually attempting to help us move in that direction. By determining the size of the tab we do and the amount of deflection it has for the amount of elevator deflection, we can control the amount of servo action or helping action that we want to do in it. Now that's a case where if you have an elevator that's quite heavily loaded and you want to use a servo tab to reduce the actual effect of the stick forces, you can. Now this same tab can actually be your regular trim tab too. In other words, this linkage that this thing mounts on to the stabilizer in here, by doing that, can be such that it's also adjustable. So you can adjust it into this position, and now the force is being neutral as you trimmed it, but yet every time you move it, it moves along with you. You can use servo tabs on ailerons, you can use them on rudders. There's a variety of control surfaces you can actually put these servo tabs on. The opposite of that is an anti-servo tab, and then that is, and what they say about that is instead of it helping you, it would go this direction and actually add additional forces. Rarely would you ever want to use an anti-servo tab on an elevator or even on an aileron. Only if you want to increase stick forces would you do that. When we get to an all-flying tail, then that's a different story. Then we want to use an anti-servo tab, but for a real good reason. And we'll cover that when we get into that section of the thing. Another type of thing you can do is you can use a spring tab. A spring tab would be very similar to a servo tab. You'd maybe hook it up exactly the same way. The difference is that you use a spring actually in part of the linkage. And what the spring is going to do, it's essentially going to sense the speed of the airplane. In other words, let's say you have an ordinary elevator that moves up and down, and you put this little servo tab so that when you pull back on the wheel, the elevator went up, the little tab came down and helped you move it. Now let's say you got a spring that's hooking together, and let's say this spring is set at a certain number of pounds of force. Well, at load speed, 60, 70, 80 miles an hour, the forces on that tab are so low that it hasn't even moved the spring. So therefore, it acts just like your regular servo tab would act. But let's say you're doing 200 miles an hour now, and you go to move the wheel. Now what has really happened is, that's little tab back there knows it's got 200 miles an hour of air pressing against this. So as the elevator came up and the tab would have deflected, let's just pick numbers here for example. Let's say you move this thing 10 degrees, and let's say that tab came down 10 degrees compared to this. Well, if you're doing 200 miles an hour, the forces on that thing might be such that it stretches that linkage, which is nothing more than a spring that you have. As it stretches it, it won't allow the tab to be 10 degrees deflection. It might only allow it to be 5 degrees deflection. So what has it done here? Well, it has reduced the amount of help that the servo tab is doing to reduce your forces. So therefore, by using a spring tab, you can have higher forces at low speed and less forces at higher speed, relatively speaking. I don't mean to say that at 80 miles an hour you got 10 pounds for every movement, and at 200 miles an hour you only have 5 pounds. No, no. What I'm trying to say is, with the servo tab working fixed, you might have 10 pounds of force at 80 miles an hour, but at 200 you might have had 60 pounds, and that's too much if you just use the direct ratio. But because the spring is there, you'll only have 40. So now you've gone from 20 to 40, and all of that feels good. Working with spring tabs is a little bit tricky. There's some other characteristics and consideration you have to do about it. And generally speaking, this is, I don't want to say last resort system you put in an airplane, but it's not necessarily something you want to design right from the beginning, because there's so many things you can do to get to the point where you don't need a spring tab that it's not something that you should initially plan, and there are other ways to do it. Once you have a design, and once you're flying your airplane, and now you find your forces are way too high at high speeds, but nice at low speeds, this is a place where you may not want to adjust the size of your servo tab or adjust the amount of deflection, but instead you want to put a spring tab inside there. This is something that you would consider when you really get into airplanes that are doing like 300 miles an hour, 400 miles an hour, World War II type fighter airplanes, or some of the high performance light twins of today. Besides those items, we can do something else. We can work with the trailing edge bevel, as it's called. Now let's redraw this picture a little bit here. I'll just make a larger view of the elevator position. The angle of the trailing edge itself, that very small rear portion of this elevator, has a pronounced effect on your stick forces. If you make it very sharp, literally like that, you can increase the hinge moment forces quite a bit, the stick forces. In the Bede 5, that's something we actually wanted to do. And maybe in a sailplane, that's something you want to do. But generally, on a powered airplane, you don't want to do it. But let's say we went the other way. Let's say we brought the surface down and we beveled it like this. This bevel here has a very, very strong effect in reducing the hinge moments on it. For example, if the angle between here was 10 degrees and you make it now 20 degrees, which isn't, I've exaggerated on this little sketch here, 20 degrees isn't that much more, you will more than reduce the forces by more than half. You can reduce it significantly. You can actually make the bevel big enough here to where your forces are almost zero. You can get it down to pretty low values. I've seen airplanes where the rudder, for example, it can be done on rudders, it can be done on ailerons, it can be done on elevators. But the surface has already been designed and built, and then what they'll do is insert a round piece of tubing sticking out the back end. Now this tubing sticking out, that's doing pretty much what this bevel will actually do. It will act in the same way, but instead of retooling for the whole elevator to get a thicker and then a bevel portion out of it, you can insert this little piece of round tubing in there. It doesn't look real good, and it really hasn't given you that much more drag because the boundary layer is fairly thick by the time it gets back into this rear portion in here. But if the forces are high and you need a fix and something to correct the measure that you have that's somewhat of a problem, this is a way to consider doing that. It's very common on ailerons. I think a Mooney Mark 20s, for example, if you look at their ailerons, they're designed right from the beginning to be sort of thick like this and then bevels on down in here. Now this bevel portion, that may only be 2 or 3 inches of the aileron itself or the elevator. This works for ailerons, it works for elevators, it works for really any of the trailing edge control surfaces you want to do. Another factor to be considered is that the control forces, the hinge moment itself being linear, is what you're striving for. But if you have a stabilizer elevator airplane and you adjust the stabilizer, let's assume the stabilizer is an adjustable one instead of the trim tab one, or let's say you do have a trim tab on it and you adjust it. Let's assume under some kind of configuration you might have that the, yeah, let's erase this and take a look at it. Let's assume you have a stabilizer and an elevator that are trimmed this way. You use a tab or whatever, you adjusted this thing, and the airflow is in this direction. So now the stabilizer elevator is flying at a deflected condition at a given angle of attack. This variation of the hinge moments in here as compared to different angles of attack will not be linear anymore. In fact, you can get a situation where it'll start to become almost somewhat of a reversal on a thing. So you have to look at all of this and be somewhat concerned about the fact that if you have a stabilizer elevator, and if you're going to be adjusting the stabilizer or flying at significant deflection